Hello everybody. In the previous deliberations we had discussed the need of machine language, the T-states, the addressing modes, and also we had discussed regarding the grouping of instruction set. Every digital computer like the one we have here can be made up of these four blocks consisting of input, CPU, output and memory. The instructions which we have are clubbed into various groups. Today we are going to discuss two groups, that is the data transfer group of instructions and the arithmetic group of instructions. The data transfer group of instructions involve the movement of data from register to memory or memory to register, whereas the arithmetic group of instruction carry out the function of addition and subtraction. When the data transfer group of instructions are executed, no flags are affected. The instructions that form the part of data transfer group of instructions are move, MVI, which can be clubbed together, LXI, LDA, LHLD, LDAX, which can once again be clubbed together, STA, SHLD, stacks, which can be treated as one group of instructions, and a last group which is consisting of XCHG and SPHF. Now let us see what are the various operations that are carried out when the instruction move and MVI are implemented. For execution of move instruction, the program counter of microprocessor places the address MMMM on the address bus. The contents of program counter are automatically adjusted to point to the next memory location. Opcode of move is fetched from MMMM location of the memory and is copied in the instruction register. The opcode is decoded and data is transferred from source register to the destination register. This instruction requires one machine cycle of 4 T-states for implementation. In move D, M instruction, the program counter contains the address MMMM of memory location having the opcode. The program counter is incremented automatically. The opcode at the location MMMM is copied in instruction register. The instruction is then decoded. The control unit places the contents PPQQ of HL register pair on the address bus. The data XX at PPQQ location is copied in the destination register. As we have observed in these two instructions, the sequence of placing the contents of program counter on address bus, incrementing the program counter, copying of the opcode from memory to instruction register, and its decoding are common. In fact, they are common to all instructions of 8085 microprocessor. In move M, S instruction also, the opcode of the instruction is copied in instruction register and decoded. The control unit places PPQQ from register pair HL on address bus and copies the contents of the source register to address memory as XX. The memory with address PPQQ receives the contents XX from the source register. In MVI register data, the data YY is picked up from memory location MM+1 and is copied to specified register. Now we take the subgroup consisting of LXI, LDA, LHLD and LDAX. The instruction LXI involves the copying of data which is a part of the instruction into the specified register pair. LDA address means copy the contents of the memory location whose address is available in the instruction to the accumulator. LHLD means copy the contents of the memory location which is specified as a part of the instruction to the register L and of the next memory location to the register H. LDAX RP means load the accumulator with the memory location whose address is available in the specified register pair. After decoding the opcode, the program counter places the address mm+1 on the address bus and copies the contents, that is QQ, into the lower register of the destination register pair. The program counter once again places the next address, that is mm+2, on the address bus and copies its contents, that is PP, to the upper register of the specified register pair. Finally, after the execution of the instruction, the program counter contains mm+3 as the next address. In LHLD address, after decoding the opcode, the control unit picks up the contents PPQQ from mm+1 and mm+2. Using PPQQ as address, control unit copies its contents XX to register L and that of PPQQ+1, that is YY, to the register H. Let us see the instruction STA. This copies the content of accumulator to the specified memory location, which is the part of the instruction. SHLD address means store the content of register pair HL to the memory location, which is the part of the instruction. The contents of L go to the address, which is a part of the instruction, and the contents of H go to the memory location, which is next to that. Stacks RP means store the contents of accumulator to the memory location whose address is specified in the register pair. Let's see the actions that take place when these instructions are executed. After decoding the opcode, the contents PPQQ from mm+1 and mm+2 are used to point to the memory location, where contents YY of the accumulator are copied. For execution of stacks RP instruction, the memory address PPQQ is picked up from BC or DE register pair and is placed on the address bus. The contents of the accumulator, that is YY, are copied to this address memory location. The remaining two instructions are XCHG and SPHL. The XCHG instruction and SPHL do not have any operand. The function of XCHG is to exchange the contents of register pair DE with that of HL, and the function of SPHL is to load the stack pointer with the contents of the HL register pair. When these instructions are executed, what actions take place? Now we can view that. This instruction is used for non-destructive exchange of data between register pairs DE and HL. The contents PPQQ of register pair DE are moved to HL and the earlier contents of HL are moved to register pair DE. In SPHL instruction, after decoding, the contents of register pair HL, that is PPQQ, are copied to the stack pointer SP. At this stage, we are in a position to use the instructions of data transfer group and solve some problems. The first problem we are going to take up is to load accumulator with data 82H and save it in register B. The solution for this problem is MVI A, 82H, and the second instruction we have to use is move B, A. The first instruction copies 82 into accumulator, and the second instruction copies the contents of accumulator to register B. The second problem, which can be solved using the instructions of this group, is write instructions to load 885 in register pair HL using MVI and LXI instructions. I'll first take the MVI instruction. In this case, we can load one byte at a time. The first instruction for this is MVI H, 80H, and second instruction is MVI L, 85H. The first instruction loads 80 into register H, the second instruction loads 85 into L, thereby giving us 8085 in register pair HL. The second instruction is LXI. In this case, we have to just say LXI H, the data which is required to be loaded, which is 8085, and the result of this is that HL register pair contains 8085. The next problem which we can tackle using this set of instructions is memory location 2040 holds the data FFH. Using move LDAX and LDA, copy this data to the accumulator. In order to use the move instruction, we have to move the data from memory location to the accumulator. For that, we have to first create a memory pointer. The memory pointer can be created by using the LXI instruction, that is LXI H, 2040. The next instruction we have to say is move A, M. The result of the first instruction is to load into register pair HL 2040, and the second instruction copies the contents of that location to the accumulator. The second instruction which we have to use here is LDAX. In this case, the address from where the data is to be picked up is to be brought into a register pair. Let us use the register pair B, and we can say LXI B, 2040. This means we are copying 2040 into register pair BC. The moment this is available here, what we are required to do is we are required to load the accumulator with the data which is available in the register pair 2040. The third instruction which we have to use here is the LDA instruction. In case of LDA instruction, the address from where the data is to be picked up is to be written straight away in the instruction, and that instruction could be LDA 2040H. This loads the accumulator straight away with the data which is available at 2040. The last problem we are going to tackle here is that register B contains AA. Copy it to location 4000H using move, STA and stacks. Once again, in this case, we have to use the move instruction. When we have to use the move instruction, we have to first create the memory pointer. The memory pointer can be created for this particular problem by saying LXI H, 4000, and the data is available to us in register B. Now, in order to copy the data from register B to the memory, we have to use the instruction move M, B. What it actually amounts to is we are copying the contents of register B to the memory location which is being pointed to us by the register pair HL. The second instruction we have to use is STA. For STA, what we require is we have to just give the address where the data is to be stored, but the data is required to be there in accumulator and not in register B. So we'll have to first move the data into accumulator, and then we can say STA 4000H. The result of this is that B has been brought into A, and from A it is being transferred to the location 4000 as is desired by the problem. The third instruction which we have here is STAX. Now, in case of STAX, we require the address to be made available in a register pair. Since we are already using the register B, so we'll create another register pair in which we'll store the address. Let us say LXI D, 4000H. So this becomes the register from where we have to pick up the address. Once again, this instruction STAX works with the accumulator. So we have to bring the data into accumulator, and that can be done by saying move A, B. Once the data is available in the accumulator, we have to just say stacks D. The result is that the contents of accumulator are going to be stored at the memory location which is being pointed by the register pair DE. With these problems, I think all of you are in a position to tackle simple problems using the data transfer group of instructions. And now what we are going to do is the arithmetic group of instructions. Unlike the data transfer group of instructions, the arithmetic group of instructions affect all the flags. That is the zero flag, the sign flag, the auxiliary carry flag, and the parity flag. The 5 functions that can be carried out by the arithmetic group of instructions are addition, subtraction, increment, decrement, and a special function of decimal adjust accumulator. In addition, we have got all these statements available. You can see here that one of the data is assumed to be in the accumulator, and the second data is going to be either in the specified register or memory location, or is going to be part of the instruction, or is going to be available in the register pair. Once these instructions are executed, the result is going to be available once again in the accumulator. Once these instructions are executed, what actions take place, that we can see now. To refresh the sequence of actions that we had observed for execution of earlier instructions, the program counter contains MMMM. The contents of program counter are automatically incremented. The MMMM is placed on address bus, and the contents of MMMM are copied to the instruction register IR. In this instruction, opcode is decoded and the source register is identified. The contents of the accumulator, that is XX, are added with the contents YY of the identified register, and the resultant, that is XX plus YY, is stored back to the accumulator. In ADC-M instruction, the register pair HL contains PPQQ, which is the memory location from where the data YY is picked up, and this is added to the contents of accumulator along with the binary value of the carry flag. The resultant, that is XX plus YY plus C, is stored back in the accumulator. In ADI data instruction, the contents of MM plus 1 memory location, that is YY, are added with the contents XX of the accumulator, and the resultant, that is XX plus YY, is stored back to the accumulator. In ACI data instruction, the contents of memory location MM plus 1, that is YY, are added with the contents of accumulator, that is XX, along with the status of the carry flag. The resultant XX plus YY plus C is stored back in the accumulator. DAD RP is the only 16-bit addition instruction available in 8085 instruction set without the use of accumulator. The contents YY of the specified register pair are added to the contents XX of the register pair HL. The result is stored back in the register pair HL. DAD affects only carry flag. The subtraction has got 6 different forms of instructions available to us. When a subtraction is to be carried out, one of the data is assumed to be in the accumulator, and the second data is going to be provided either by the specified register or the memory location, or by the data which is a part of the instruction. The subtraction which is carried out using these instructions is a special type of subtraction, that is using 2's complement method. Once these instructions are executed, what actions take place can be viewed now. The control unit picks up PPQQ from register pair HL as the address from where the data YY to be subtracted is picked up. YY is then subtracted from the contents of the accumulator, that is XX, and the result is stored back in the accumulator. The subtraction is implemented using 2's complement method. In SBI data instruction, the data YY is picked up from MM plus 1 and is subtracted from the contents XX of the accumulator along with the binary value of the carry flag. The resultant is stored back in the accumulator. The instructions which form the part of increment are special type of addition instructions. They increment the contents of the specified register or that of the memory location or the contents of a register pair by 1. No flags are going to be affected when these instructions are executed. At this stage, if we execute these instructions, what actions are going to take place can be viewed now. In INR R instruction, decoded opcode is used by the control unit to identify the register which contains data YY. The contents of the specified register are incremented by 1. The result is available in the specified register. This instruction does not affect carry flag. In INX RP instruction, on decoding the opcode, the register pair is identified. The contents YY of the specified register pair are incremented by 1. The result is available in the specified register pair. This instruction does not affect any flags. The instruction under the category of decrement are special type of subtraction instructions. They decrement the contents of the specified register by 1 or that of memory location by 1 or that of register pair by 1. Once DCR instruction is executed, the 0 flag is affected. No flag is affected when DCX instruction is executed. At this stage, if you view the action, they will be like this. In DCR M instruction, register pair HL contains PPQQ, which is the address of the memory location where the data YY is stored. The contents YY of memory location PPQQ are decremented by 1 without affecting the carry flag. The result is stored back in the memory location PPQQ. DA instruction is a special instruction as it takes the help of auxiliary carry flag in carrying out its action. What it does is, it takes the 8-bit data which is available in the accumulator in the form of binary number and converts it into two 4-digit BCD numbers. What actions take place can now be seen. This is a special instruction which is used in case of BCD addition. It picks up data which is available in accumulator and converts the same into two 4-bit BCD numbers. The microprocessor checks the lower 4 bits of accumulator, and if it finds it to be greater than 9, a value 6 is added to the accumulator. Now, if either the upper 4 bits of the accumulator have binary value greater than 9 or auxiliary carry flag is set, a value 6 is added to the upper 4 bits of the accumulator. Let us now take some problems of addition in which we are going to use instructions meant for the purpose of addition. The first problem we have is that the contents of accumulator A are 93H and the contents of register C are B7H. Add both the contents. For this we'll have to use the instruction add C. In this case, one of the data is automatically assumed to be in the accumulator. The data has already been written here, which is 93 in the accumulator and B7 in the C. The addition is carried out in the fashion of binary addition. When 1 and 1 are added together, the result is 0 with carry as 1. With 1, 1 and 1, the result is 1 with carry as 1. 1 and 1 give us 0 with carry as 1. 1 with 0 and 0 gives us 1 here. 1 and 1 added together gives us 0 with carry as 1. 1, 0 and 1 gives us 0 with carry as 1. 1, 0 and 0 gives us 1 here, and 1, 1 here gives us 0 with carry as 1. Initially the carry was not there, now a carry has been generated. So the carry flag now becomes 1. The result of this is that the answer we have available here is 4 and A followed by H. This H indicates that we are using hexadecimal number systems. Now let us see the flag status. Since the D7 bit is 0, the sign flag is 0. Since after the addition the result is not 0, the 0 flag is 0. After the addition of the two numbers, we had generated a carry, so the carry flag is 1. Now let us go over to another problem which is in continuation to the problem I am already discussing with you, whereby I would show to you the importance of observing the status of the flags. The problem is to add the numbers 35H directly to the sum in the previous problem when CY flag is set. The answer we had earlier was 4A. The carry flag is set here. The binary equivalent of 35 is 0, 0, 1, 1, 0, 1, 0, 1. And since 35 is to be added directly, so the instruction I am going to use is ADI 35H. This instruction automatically assumes that one data is available in the accumulator. Once we carry out the addition of 0 and 1 gives me 1, 1 and 0 gives me 1, 0 and 1 is 1, 1 and 0 is 1, 0 and 1 is 1, 0 and 1 is once again 1, 1, 0 is 1, 0 and 0 is 0. Now, after having seen this, the result we get is 7FH. If we try to observe the status of the flags now, you can see here, since the D7 bit is 0, the sign flag is 0. Since the result is not 0, the 0 flag is once again 0. Whereas after having added 4A to 35, the carry flag, which was earlier 1, has been reset to 0. The result is that we are getting CY as 0. Although practically speaking the carry flag should have been there, yet it has been lost because we did not take care of the carry flag earlier. At this stage we can go and see the problems which can be carried out using the increment and the subtraction instructions. From this example which we are going to tackle now, you will be able to appreciate the difference between the INR and the add instruction. The problem is that register A contains FFH. Illustrate the differences in flags set by adding 01H and by incrementing A. For this, if I take the instruction ADI 01H, then accumulator already contains FF whose binary equivalent is 1, 1, 1, 1, 1, 1, 1, 1. To this, if I add 01, the result would be 1, 1 would become 0. I'll have a carry which will be 1. To this, if I add 1, I'll have 0 with carry as 1. 1, 1 will give me 0 with carry as 1. 1, 1 will give me 0 with carry as 1. 1, 1 will once again give me 0 with carry as 1. 1, 1 once again will give me 0 with carry as 1. 1, 1 added together will give me 0 with carry as 1. If I add 1 and 1 here, I'll have 0 with carry flag being set to 1. Let us see the status of the flag after we have carried out the addition. Since the D7 bit is 0, that indicates that the sign flag is 0. After we have carried out addition, the result is 0. That indicates that the 0 flag would be set. As far as CY flag is there, we have already seen that it is already 1. This is the status of the flags after we carry out the add instruction. On the other hand, if I carry out the INR instruction, the status of the flags would be something like this. The sign flag would be 0, the 0 flag would be 1, the carry flag would be 0. Now the difference between the two instructions is that after incrementing, the contents of accumulator would become 0. As such, the Z flag is 1, CY flag is not affected by the INR instruction, and sign flag is affected as has been shown here. This is the basic difference between INR and add instruction. Let's take the next problem, which will explain to you the subtraction procedure. The problem is that register B has 65H and the accumulator A has 97H. What we require is to subtract the contents of register B from the contents of A. In this case, 65 is to be subtracted from 97. So 65 is the subtrahend. So the first step which is required is that we write down 65 in binary fashion, that is 0, 1, 1, 0, 0, 1, 0, 1. Then we find out 1's complement. The 1's complement of this number, that is 65, is for 0 we write 1, for 1 we write 0, and accordingly we get 1, 0, 0, 1, 1, 0, 1, 0. The second step involved is to add 1 to this number. When we add 1 to this number, what we get is 2's complement. So when we are adding the number 1, we have 0, 0, 0, 0, 0, 0, 0, and 1. The result is addition of 0 and 1 gives me 1, 1 and 0 gives me 1, 0 and 0 gives me 0, 1 and 0 gives me 1, 1 and 0 gives me 1, 0 and 0 gives me 0, 0 and 0 gives me 0, 1 and 0 gives me 1. So the 2's complement of 65 is 1, 0, 0, 1, 1, 0, 1, 1. The next step is to implement the subtraction of 65 from 97. And this is achieved by what? We have to add 97 to the 2's complement of 65. 97 is 1, 0, 0, 1, 0, 1, 1, 1. And the 2's complement is already available to us in the form of 1, 0, 0, 1 and 1, 0, 1, 1. So when we carry out the addition, 1 and 1 gives me 0 with carry as 1, 1, 1 and 1 gives me 1 with carry as 1, 1 and 1 gives me 0 with carry as 1, 1 and 1 gives me 0 with carry as 1, 1, 1 and 1 gives me 1 with carry as 1, 1 and 0 gives me 1, 0 and 0 gives me 0, 1 and 1 gives me 0 with carry as 1. At this stage, the next step involved is to complement whatever is the carry's condition. So condition of the carry is right now 1, so when we complement it, it becomes 0. Rest the contents of accumulator do not change. So 0 remains as 0, 1 remains as 1, 0 remains as 0, 0 remains as 0, 1 is 1, 1 remains as 1, 0 remains as 0, and 0 remains as 0. So the result after we have subtracted 65 from 97 is 32H, that is 0, 0, 1, 1, 0, 0, 1, 0. Now let's look at the status of the flags. Since the D7 bit is 0, the sign flag is 0. After carrying out the subtraction procedure, the result is not 0, so the 0 flag is 0. And since the carry flag was 0, this is being shown as 0 to you. These instructions have given an insight to the arithmetic group of instructions. The role of data transfer group of instruction and arithmetic group of instructions is clear to you now. While making a choice as far as the instructions is concerned, you must always keep in your mind the number of bytes that are available, the number of t-states, and the machine cycles. I hope all these things will always help you in making a proper choice, and you will be able to do the job properly.